This is going to be a joint presentation by Bill and me. Basically, I'm going to stand up here and give you the broad generalities of the arm-waving stuff, and Bill's going to give you the real science. That's why we're a good combination. First off, some basic facts about the delta. I'm going to go through this. This is stuff you all know, but I like to remind people of it. First off, the delta does have a diverse fish fauna. About 50, 60 species, depending on who's counting, have been recorded from the system. 26 of them common enough so you can do real analyses of their biology. But half of them are non-native species. So that's also always important to keep this in mind. We have a diverse fish fauna, but half of it don't belong there, at least not historically. They do now. And so this means two things. One is the delta is always going to have lots of fish, and there's always going to be an ecosystem out there. We tend to forget that, especially when you talk about delta ecosystem collapsing and so forth. It's also good to always remember these fish have clout, especially the endangered species. Judge Wanger's ruling in September 2007 certainly should always remind you of that, about how rapidly things can change if we don't do something about the fish. And we do have, 5 endangered species out there, another one on the way if the longfin gets listed. But we also forget that there's more than fish that are listed out there. This is from the latest Delta Science Report. It's a very nice graphic. We have a lot of invertebrates, mammals, plants, and so forth that are also endangered out there that may be on the islands that we're flooding, or we're talking about flooding. We also should always keep in mind that the delta is currently a poor habitat for the fishes we care about. And that's as reflected in the pod, striped bass, delta smelt, longfin smelt, and so forth. And we're seeing these fish declines. The salmon fishery has also collapsed recently. That's obviously not entirely the fault of the delta, but the delta is playing a role in that, the conditions in the delta. So again, just keeping these things in mind, I think, is always important when you're talking about the fish. And as I think you've heard repeatedly today as well, the delta cannot be maintained in its present configuration. But that's not necessarily, I say, which is bad for fish. It's the present configuration which is bad for fish, as Bill will talk about. Changing it is not necessarily bad. That's what's so interesting. And, of course, we have this idea that major change is on its way. You've heard lots about this. I'm going to go through my little recipe for major change. You got these usual ingredients of subsiding land, rising sea level, more frequent floods, weak levees. You mix them together, you shake well, and you add some water, and you get more aquatic habitat. And that's something that from a fish perspective, it's really important to keep in mind. Depending on various scenarios, we are going to have more aquatic habitat out there. And there are going to be fish out there in that aquatic habitat. The key question is, are they the fish that we care about, that we want to be out there? And again, Susan Marsh is always on the sidelines from all this. I'm hoping that we can, in the next few years, we can give it more attention. But Susan Marsh is obviously going to be changing in major ways as well. It's going to become a really good brackish water habitat, a lot of it's subtidal, and that's probably going to change in ways that are positive for fish. This is one of Chris Enright's elevation diagrams showing you how much of it's below sea level, and how, in fact, if the delta has weak levees, Susan Marsh has them in spades. This is very low. You go out there in a high tide, a lot of them already spill over. In our Appendix D, then, keeping all these things in mind, we ask 4 basic questions that we attempt to provide answers for. First off, what species are most desirable? The other is, what species do we manage for? Because we're making choices. With 50-plus species out there, we are essentially choosing which species we want to have around in the future, or to be really abundant in the future. And we also are asking, how are the fishes affected by ecosystem change, especially the species we think are desirable? Then how will the water export alternatives affect the fishes? And what actions then can improve the delta for desirable fishes? These are all big questions, and we've provided best partial answers. So, which species are the most desirable? Well, it's pretty obvious that the threatened and endangered species are high on everybody's list. We have no choice. The Endangered Species Act says we have to maintain their populations and have to manage the system for them. There's a general agreement, not by everybody, but the native species are also contribute in a big way to the species what we consider to be desirable. Most of these are endemic to the Central Valley, so it provides even a better reason for protecting them. Fish that support fisheries are also high on the list, although different people have different priorities for species. Largemouth bass versus striped bass, for example. And another characteristic of the desirable species are those that are estuary independent, that need the estuary to exist. We have a lot of the species out there today, as Bill will show you, are not species that need the estuary. They can exist in lots of other places, but the species that we need to, that from one perspective that are most desirable are those that depend on the estuary one way or another, and that includes some non-native species. So one way to look at this then is to rank species from 0 to 4, undesirable to desirable, and look at the
Probably better if you use the mouse, because then the webcast will show.
Oh, okay. Okay, here we go. Okay, so from 1 to 4, the listed species clearly are desirable by these categories. And estuary-independent species also high, by the way I'm talking about. So you can start assigning ranks to species in terms of whether you want to manage for them or not, which is, of course, what we've been doing. And here's essentially a list of some of the most desirable and some of the most undesirable fish. And the language is deliberate, desirable versus undesirable. It's not science. It's based on some societal characteristics that we've chosen. So delta smelt, longfin smelt, green sturgeon, steelhead, spring chinook, winter chinook, these are all listed species or close to it. And the undesirable species are things like largemouth bass, carp, wagasaki, inland silversides, bluegill. These are all non-native species that are really abundant in the present delta. And the idea is to shift the delta away from these species over to these species. Again, this is not, that while you can do this based on science, the choice of species is a choice we're making as a society. So one of the big questions then is, do these fishes fall into ecological clusters? Because species management is not the best way to go. So one of the first questions we asked on this is, do these species fall into ecological clusters? And this is where Bill will have some answers for you.
I'm not sure about that, but just the pointer here. Oh, I'm just using the pointer.
They won't be able to see it on the web, so if you move the mouse, you'll have it.
Oh, okay. Got it. Okay, cool. All right, so, well, Peter really has the answers. All I really did was look at the paper we were writing and realize that all Peter really had were pictures of fish, and I thought we might want to have a graph or two. Now, I'll leave it to you to judge whether this is more formal or not. But all I'm really doing here is trying to find a way to partially formalize some of the ideas that are out there, many of which data for really, proving and disproving are somewhat lacking or will be difficult, if ever, to get. So given that the environment is going to change, are there subgroups of fishes that are most likely to change together? And if we do promote different aspects of the environment, can we push it more towards those types of attributes that so-called desirable fishes prefer? And to do this, basically what I did was look at the life history characteristics of about 17 species. And life history characteristics shown here on the column on the left, things that some of which are known, some of which we had to kind of guesstimate, but things such as lifespan, size at maturity, fecundity, and also habitat, the degree to which they use salt water versus fresh water. Generation time is a very important one, how long they live. Temperature. Temperature is obviously very important and discussed quite often in context of climate change. And the types of habitat. Are they open water species? Do they prefer geria beds? And you put these together for 17 species that we used, and you can formalize this by putting it into a multivariate analysis. Where I usually did here was principal components analysis, very simple. And when you do that, you get these components. And basically what it does, it takes the variability and all the life history characteristics among the species and repackages it, putting it into patterns of variability amongst the species which relate most closely to each other. So basically with these coefficients on this index tell you which species, which characteristics these indexes are emphasizing. This shows the breakdown and the variability explained by the indices. And basically, three components, the first three, tend to explain better part of 80% of the variation in the data set. So it's captivating most of the variation and can be used to potentially show how these species are corresponding with regard to one another. These are relating the indexes PC1 versus PC2 and principal component 2 versus PC3. These things can be interpreted. PC1, which is pretty much the norm for a principal components analysis, relates fishes that are either big, long-lived, short-lived, low fecundity types of things, so big and small here, basically. And here we have more of a habitat thing. You know, are they anadromous? Do they move around? Do they like salt water? Are they resident? Do they like fresh water? Broad patterns. These components are a little more subtle. PC2, here again, is this one, salt versus fresh. And here we have a more subtle habitat use. Do they like open water? Are they broadcast spawner? Or do they like aquatic vegetation and more freshwater habitats, more parental care? And the gist of this is we see these clusters that basically pull out delta smelt and longfin smelt by themselves. More of the anadromous species we're familiar with here, king salmon, striped bass, American shad. And directly opposed to this, we have all the freshwater species that utilize Egeria. Largemouth bass, all the sunfishes. And so we can see that just based on life history characteristics and how they use the delta environment, we see that really are the fishes correspond basically oppositely to the environmental conditions out there. So if we were to promote Peter's desirable fishes, in this context, we would want to be having more saline, open water habitat, which seems to be on its way. So this is sort of a summary of the groups. Are there management clusters in these groups where if we push or nudge the environment into a certain area, are we going to promote or basically foster some of these other species? And we basically get the native smelts, the planktivorous fishes, mostly undesirable, anadromous fishes, salmon, striped bass, American shad, slough residents, and benthic fishes. Now if we relate that plot with regard to Peter's desirability index, we again show principal component 2 versus principal component 3. And here's Peter's desirability index on a 1 to 5, 5 being most desirable. We see it falls out pretty close, pretty nicely. And most importantly, what we see is that there's a real difference between, basically, the most desirable fishes and the most undesirable fishes are clearly opposite each other in multivariate space. So basically what it suggests is that if we promote the system to be more saline, more variable, and more open water, we will promote the desirable fishes. If we have it basically looking like a lake in southern Arkansas with Egeria beds and all these things, we will be promoting fishes that live in southern Arkansas, which is what we're doing. So, given this sort of static approach, how have these types of groups of fishes changed over time? And to look at this, I thought about this for a while, and I decided it just reminded me about when I was a research assistant as a bachelor. I used to make what they call phase plots for theoretician Richard Levins. And it seemed to me that relating the delta, the history of the delta, the way we talk about the delta, we always talk about it's a very different place. It's changed to a different sort of state. And it seemed to me like a regime shift. And so what I'm going to do is couch what has gone on in the delta over the past 40, 50 years in the context of regime shift theory. Now, regime shift theory is actually pretty well developed. In the ecosystem context, the concepts come from the behavior of dynamical systems. So it's pretty well thought out, where a regime shift can be really thought of as the interplay, the interaction between two types of processes. Ones that are external, moving relatively slowly in time, and internal forces that act relatively quickly. Now in the delta, what I'm going to propose that the external slow factor is the changes in habitat and export levels and export policies that have gone on over the past 40 years, whereas the internal fast processes are sort of the sudden increase and rise of exotic species. Resilience is really the capacity of a system to absorb disturbance and reorganize itself back again into its same properties. There's two aspects of it there. One is how fast it does it, and the other is how much does it look like the system it left. Hysteresis is an interesting concept. It's once you shift to a different regime, and even if you shifted the conditions back to their original condition, sometimes you have to push the system much harder in order to make that regime shift reverse itself. So regime shifts can get sticky. You can get stuck in places because the internal configurations in the new regime change and may resist that change. In other words, have high resilience. So in the context of these things, what has gone on in the delta? To do that, I put together some trends. I put together trends in water exports, salinity, water clarity, two pod species, delta smelt, striped bass, an exotic species, inland silverside, one of our undesirables, and two centrocket species, the undesirables, largemouth bass and bluegill sunfish. The fish data I got from the U.S. Fish and Wildlife Service Beachsane survey. Why? Because it was the one survey where all types of open water versus more shoal or bottom fishes can be caught in one survey. Equal opportunity. The water exports from day flow and salinity and water clarity came from the TONET survey. Now all these data come from July to September, which happens to be the most critical time or pressing time for fishes in the delta. The conditions are much tighter there. Fish biomass is at its highest levels. You have all the juvenile fishes around, water temperature elevated. And so salinity and water clarity I got from the TONET survey, which occurs at that time, and that is taken for juvenile fishes. And so all of these come from delta-only stations. And when you do that, you see some very interesting trends, trends that we tend to usually talk about and think we know. But here they were. Increase in water exports in the summer. We always talk about increasing exports. We talk about decreasing salinity in the delta. We see an increase in water clarity. And, you know, our favorite fishes have crashed. We obviously knew that. At least we thought we did. Exotic species have increased. This is inland silversides, tremendously increased. And centrocket species have increased. All right? So here are these patterns. So in order to relate these things, the idea here is to see how these different components of the ecosystem have changed over time with regard to each other. So in order to do that, what I did was standardize each of these variables to a zero mean, unit variance, because we're more interested in how they have changed over time rather than absolute values. And when you do that and you plot them together in these phase plots, you get patterns that look like this. And so let me walk through this. Basically, over time, if we increase water exports, what we see is delta salinity decreases. The red, I should say, the numbers here represent years. And this goes from like 1976, I believe, to 2006. The red shows the last 10 years, or from 2001 to the present. Okay? Now, the only real take-home message from this is that in each of the graphs, in the past decade, we've lost variability. Right? All the points are clustered very closely together, unlike previous years. For example, here's 76 and here's 77, right? 2 drought years, okay? But look at all the points now. And in many cases, some cases, they actually cycle. 2001, 2, 3, 4, 5, 6, and these cycle here. 01, 2, 3, 4, 5, okay? Very akin to neutral stability in dynamical behavior. So, this to me looked like fairly decent evidence for a regime change. Now let me walk through it. Increase in water exports. We get to about the year 2000 and we see a dramatic drop in salinity as well. The delta's fresher in the summertime. Right? Delta salinity here. Basically, delta salinity got fresher, as we've shown here. When we did that, we also see an increase in water clarity. Now, part of that is due to upstream issues, and part of that is due to ecosystem engineering by Egeria, right? Brazilian water weed. And these changing conditions have promoted fishes like centrarchids, okay? Over time, in the last decade, we see centrarchids have grown highly abundant. And we see that pod species, delta smelt and striped bass, have declined dramatically. Inland silverside increased dramatically. Delta smelt, down. All in this little region. Now here, we have a way to formalize the kinds of stories we've been telling about the delta now for quite a number of years. And it's very, very much resembles the dynamical behavior of complex systems in regime shift theory. So, what else does it say about, I should probably go back to that slide. So what else does this pattern say about the nature of change and how it has changed and what might happen? Well, basically what it suggests is that without this really large perturbation, maybe losing the 5 islands in the Western Delta or something, we're unlikely to move back to the system that we had. And the reason why is that funny word, hysteresis. Okay? Because most of the species that have taken hold now, I should say in dynamical terms, it would be the internal variables have gained strength. And basically what that means is things like Egeria and largemouth bass have taken a foothold in the delta. Egeria, being an ecosystem engineer, has made conditions better for itself. And things like the centrarchids, which have taken hold, are very good about living there. They have much longer generation times, things such as parental care. They're very good at setting up camp there. They're going to be really hard to eradicate from there. Certainly take an awful lot of time and effort. Much unlike delta smelt or longfin smelt, which only live a couple of years and are open water species. So these conditions are most likely to prevail even if we did shut off exports. That's the point. So now, I am going to give this back to Dr. Moyle, and he can describe his model.
Yeah, this is my kind of model here, actually generated by Jeff at one time, which is simply to say that, to say in a much simpler fashion what Bill was saying with his model, which really make this much more real, that as you go from a system which becomes increasingly fresh and less variable, you pick up more and more of the species that are regarded as problem species, like the Asian clam, water hyacinth, Brazilian waterweed, bluegill, largemouth bass. And likewise, as you go more over to the saltwater side with less variability, you pick up marine species, which actually are desirable. That's San Francisco Bay. But it's the in-between where you get these species that are adapted for the variable conditions. And that's really what we should be shooting for as we manage this system. And clearly one of the things that's going to be happening here is the delta flooding the delta islands. There's a huge amount of uncertainty as to what's going on. That's to me, one of the shocking things is the fact that we have so little information about what goes on as an island floods, even though it's been going on for a long time. What goes on in the water quality, productivity, alien species, and so forth. But Oh, thank you, Jay.
It's all about storage.
Yeah, all about storage.
Transport. Transport.
And conveyance. Storage without conveyance doesn't do you any good.
It's pretty obvious we're going to have more brackish water habitat. I think you've heard that from previous speakers, Bill especially. We're going to have the more open water habitat is obviously going to be out there. And greater habitat diversity, at least we can work towards that way. And more fish. That's the other interesting thing to me, is the idea that we will have more fish, but the question is, will they be the fish we want?